Tonight on Nova. Launched in 1977, the Voyager space probes were battered by radiation and cold. Critical equipment failed.
It's not there.
But the explorers survived, crossing the vast emptiness of space to reveal the raging storms of Jupiter, the hellish volcanoes of Io, and the secret of Saturn's delicate rings. Host Patrick Stewart takes you on a 12-year space odyssey in To Boldly Go.
Funding for NOVA is provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And Lockheed, a bold new force in systems engineering, management, and technology services for defense, space, and industry. Major funding for NOVA is provided by the financial support of viewers like you.
Imagine going eye to eye with Jupiter's great red spot, or face to face with the rings of Saturn. Hello, I'm Patrick Stewart. As the actor playing Captain Picard on Star Trek The Next Generation, I have traveled throughout the galaxy. But tonight, we're going to relive a real journey to the outer limits of our solar system. This is a model of the Voyager spacecraft that has spent over a decade exploring alien and fascinating worlds, barely visible from Earth, even with the most powerful telescopes. This mission has transformed our knowledge of the solar system and has given us breathtaking views of the outer planets and moons. Picture postcards no traveler has ever sent home before.
The story begins on August 20th, 1977. A Titan rocket weighing 1,000 tons is launched into space, carrying on its nose a small robot explorer bound for Jupiter, Saturn, and beyond. A second backup spaceship will follow in 2 weeks. It will be a journey in both space and time. On the giant planets and their icy moons, NASA scientists hope to find clues to the early history of the solar system.
Mankind seems to have a great lust to discover the origin of life and where human beings have come from and how they have developed and how they have come to be where they are. And what we have found is that we can't answer those questions by just studying the Earth itself. We have to move away from our own planet and study the other planets in our solar system.
The Voyager mission was designed to study the giant outer planets, which represent a rather different population of planets than the inner planets that we're used to, one of which we live on. We had several principal areas of investigation. We wanted to study the atmosphere of these giant planets. We wanted to study the satellite systems of these giant planets. We wanted to study the magnetic field structures, which are quite immense. And then finally, we wanted to study the ring systems of these planets.
Our Earth, the Sun's third planet, orbits in the tiny core of the solar system. Much bigger and much further away are Jupiter, Saturn, Uranus, and Neptune. Once every 176 years, these 4 outer planets line up in a way that makes it possible for a rocket launched from Earth to visit them all. That opportunity came in 1977. After studying 10,000 possible routes, the scientists picked 2 that should bring in a rich harvest of images and data from the mysterious giant planets and their moons. The Voyager spacecraft were built with the best and most rugged technology available. Out in space, they would encounter violent radiation, extreme cold, and no repair shops. They must operate for years and maintain a radio link to home across billions of miles. The radio would have to run on just 22 watts of electricity. The spacecraft had only 500 watts to power all of its activities. Since nobody knew what to expect, each Voyager was crammed with instruments to study a wide range of phenomena.
The scientific data of Voyager are sensed by these sophisticated sensors, and especially this long focal-length camera here, which is capable of seeing detail in almost as much clarity as a large telescope on the Earth, for example, looking at the moon. Here is really 3 large computers that sense its orientation, remember commands that have been transmitted up as much as a year beforehand. The way that the spacecraft is powered, since it's moving out away from the sun, beyond Mars, through Jupiter's system, beyond that to Saturn, and beyond Saturn, is with nuclear batteries, not with solar cells. The nuclear batteries, which are on this large boom here, are powered by plutonium, which produces heat. The heat is then used to drive, in effect, large thermocouples, which produce the electrical power steadily that powers the spacecraft.
The computers were large by the standards of the day, but many home computers now are 100 times as powerful. If all went well, the trip would last 12 years from launch to Neptune. A team of scientists settled in for the long haul, planning to spend an important part of their careers handling 2 machines. Hairstyles would change, political upheavals would shake the world, but the project would continue. The people and their spacecraft would grow older together. The mission was just 7 months old when Voyager 2's main radio receiver failed and the backup receiver was crippled. After a tense week, the scientists found a way to adjust their broadcast signals so the handicapped space explorer could use what was left of its hearing ability. March 1979. 18 months and 500 million miles from home, Voyager 1 is preparing to meet the Lord of the Planets. Jupiter's size is hard to imagine. 11 Earths could line up across its diameter. It has twice as much matter as all of the other planets put together. More than 1,000 Earths could fit inside. Jupiter is almost entirely made up of hydrogen and helium gas. The swirling colors come from the small amounts of sulfur, oxygen, carbon, and nitrogen compounds. There is no real surface here, nothing to stand up on, just an immense, deep atmosphere. Clouds under clouds getting thicker and hotter for thousands upon thousands of miles. The most intriguing feature that's visible on the surface is the great red spot, 3 times as wide as the Earth. It was first observed by the astronomer Giovanni Cassini more than 300 years ago. How can it have lasted so long?
In fact, what we see are these different islands of color which persist sometimes for hundreds of years. And this is a very amazing thing and very difficult to explain. Why should these fluid features exist for so long in the presence of all this turbulence, really? This movie shows motion around the red spot. You can see, for instance, spots coming over the top of the red spot, some going off to the west, some going off to the east. You can see this very turbulent region to the west of the red spot. You can see a flow down below the red spot that actually reverses direction. The existence of this very turbulent region so close to such a permanent weather feature as the red spot is very hard for me to understand.
But this computer simulation suggested an answer. It shows what happens when bands of fluids move past each other riding over bumps. On Jupiter, there's no surface, but the pressure under the clouds must be uneven, like a washboard. The simulation shows that eddies form and slowly start to merge. In the course of millions of years, the smaller ones are eaten up. This is the surviving predator. It looks something like a hurricane, only bigger. But the Earth's weather comes from a different source of energy than Jupiter's. Our weather is powered by the sun. On Jupiter, the sun is much weaker, but heat pours out from the planet's hot interior, which is still cooling off from the days when Jupiter was formed.
One of the differences between Jupiter weather and the Earth is that the atmosphere of Jupiter is continuous with a fluid interior, and also there's an internal heat source on Jupiter and not on the Earth. Now, Professor Busa of UCLA has a laboratory experiment where he takes a spherical container, puts it on a rotating platform, and heats it from within. Naturally, convection currents form, but because of the rotation, these currents are arranged in long, thin columns. Some of us think that this is what's going on Jupiter, and that this difference between Jupiter and the Earth is very important for understanding Jupiter weather.
Perhaps Jupiter's vivid bands are just the ends of cylinders which reach all the way through the planet. The Voyagers also visited all 4 of Jupiter's big moons, most of which are made of rock surrounded by thick layers of ice. These were the best photos of the moons taken from Earth telescopes. When the Voyager cameras arrived, their sharp focus revealed a history book of the solar system. Chapter 1, Callisto, the outermost moon about the size of the planet Mercury. Callisto is densely pockmarked with craters. This computer-enhanced view shows them completely covering the moon. Scientists concluded that this surface must date back to the very beginning of the solar system. The theory is that a disk of gas and dust condensed into the sun, the planets, and the moons about 4.5 billion years ago. In those early days, the solar system was full of flying debris, and all the planets and moons were subjected to intense bombardment.
This is Meteor Crater, Arizona. It's one of the rare impact craters we find on the Earth. There are, of course, many, many other craters that have been formed on the Earth and have been either eroded away or covered up by sediments. And it's only the youngest that are preserved, such as this one, which was formed about 25,000 years ago. Now, we're interested in these craters primarily because it provides us a tool for dating surfaces on the other planets and on the Galilean satellites of Jupiter. To find a surface that is chock full of craters, we must be looking at a surface that is very ancient. In fact, we must be going back to that point in time in which the rate of cratering was much higher than it is today, a time in which the pieces from which the planets themselves were built were still being swept out of the region around the planets.
The birth of today's planetary system was anything but peaceful. Bodies of all sizes were constantly crashing into the developing planets and moons. Callisto's scarred face seems to scream out this violent story. Ganymede, the next moon in toward Jupiter, was harder to interpret, but it seems to represent Chapter 2 in the history of the solar system. This moon has patches that look like Callisto, but it also has areas marked by grooves where there aren't many craters. Something happened here to erase the first craters. What was it? And why didn't it happen to Callisto? Perhaps some future explorer will give us the answer. Chapter 3, Europa. Here, all the early craters have been erased, and the surface is smooth, except for giant cracks.
Unlike Ganymede and Callisto, in which we see dense populations of impact craters on the icy surfaces, On the icy surface of Europa, we see virtually no impact record. Evidently, Europa had to remain young and active beyond the period of the torrential bombardment, so that its surface was continually being renewed. Instead, what we see are a complex network of intersecting dark bands, and they're thought to have resulted from the expansion of Europa as the ocean froze.
Europa looks very much like the cracked ice of the Earth's polar regions. This is Antarctica as seen from space. Europa just has more color. If the three outer moons tell the region's history, Io, the inner moon, turned out to be a lesson in current events. Its orange surface seems covered in hot, broken blisters, caused by volcanoes, not meteorites. Studying Io, a young scientist made a remarkable discovery.
I was doing my job of optical navigation and looking at pictures of the satellites of Jupiter and stars to tell us where the spacecraft was. I expected to see the satellite Io and 2 stars in the frame. I noticed the appearance right off the limb of Io of an anomalous crescent. I determined the latitude and longitude in the region of this crescent on the surface of Io. This turned out to be the latitude and longitude of a large heart-shaped feature on Io, already known to be a volcanic feature, but of course not ever believed to have been an active volcano. I concluded that what we were definitely witnessing was an active volcanic eruption and that the crescent itself was a volcanic plume, a dust cloud of gas, an actual volcanic eruption, the first ever witnessed on a body other than the Earth in our solar system. The other bright spot down there is also another volcanic eruption. What we are observing here in the discovery frame was in fact 2 simultaneous volcanic eruptions. The surface of Io is incredibly active, much more active volcanically than even the Earth.
We found out that not only was Io's surface being modified by volcanic processes, it was being done so literally in front of our eyes. There were active volcanoes going off at the time we were there with Voyager 1, at least 7 or 8, perhaps 9, clearly identified explosive volcanic eruptions, throwing materials hundreds of kilometers above Io's surface in the force of the eruptions. This picture shows 2 different volcanoes which are seen from several different angles to give some perspective. Here we see ejecta coming out from the center of the volcano and falling back down to the surface. Here we see it lit against black sky so that the symmetrical form of the eruption, much like a sprinkler head, and that's throwing material up approximately 70, 80 kilometers in that view. We estimate that this continual resurfacing of Io amounts to spreading a layer or blanket of volcanic material of about 1 millimeter thickness over the entire planet every year. Now that rate, if it continued over geologic time, would amount to essentially turning Io inside out.
Io's tortured activity is probably caused by its position, locked by gravity between giant Jupiter and the other moons. Powerful tides stretch and pull Io so hard that its interior melts and boils, spewing sulfur out onto the surface like hellfire in space. The Voyager scientists believe sulfur accounts for all of Io's bright colors.
We'll start out with the simple kind of sulfur you'd buy from your pharmacist called flower sulfur. It's simply yellow sulfur. As a matter of fact, on Io, at very, very cold temperatures, this yellow sulfur is virtually white. What we'll do is heat this gradually. You can see the color starting to slowly change. This is the next form. It's an orange form of sulfur. If we were to cool this very rapidly, this sulfur would retain its color. As the sulfur continues to change, it becomes redder and very liquid. So some of the flows that we see on Io, which are orange and red, suggest that this very runny form of sulfur froze, retaining the color. As we go to higher temperature now, the sulfur changes again to a deep red and becomes much more viscous, like syrup. It runs much more slowly across the surface, forming cliffs on the flow front. And then the highest form, you can start to see here, changing, is virtually a brown to black form. It's this form of sulfur we see on the black spots that are scattered around on the floors of the calderas on Io. Suggests that the materials on the floors were heated to much higher temperatures, in this case about 300 degrees centigrade.
Some of the erupting sulfur escapes Io altogether and is trapped by Jupiter's powerful magnetic field, 13 times as strong as the Earth's. The sulfur winds up as a donut of electrically charged sulfur gas, with Io orbiting inside. Voyager recorded this sound of radio waves generated by the sulfur trapped in Jupiter's magnetic field. The field generates an electric current of 3 million amperes, which flows between the Moon and the planet. Voyager also discovered a delicate ring around Jupiter, much too faint to be seen from Earth. Here it is backlit by the Sun, a preview of the next stop on humanity's grandest tour ever. As Jupiter swung the Voyagers around, its immense gravity sped them up as much as the Titan rockets that had launched them. In the process, Jupiter actually slowed down on its course around the Sun about 3 feet every trillion years. If it's 1980, this must be Saturn. Saturn is about 3/4 the size of Jupiter and much less dense. As Voyager approached, its atmosphere looked like a relatively bland version of Jupiter. But its rings were even more dramatic than the scientists had imagined and filled with surprises. For one thing, this celestial wheel has spokes.
We rather quickly created a ring movie from Voyager images, and if we can see that. The features appear as dark projections in the rings, and we'll see them rotating around. This was an absolutely startling discovery which was made. No one expected to be able to see these kinds of features in the rings. We always thought of the ring particles as very small, boulder-sized particles, which we would not be able to resolve at these resolutions. We see them as dark projections in backscattered light, and you see them rotate around. One of the things we wanted to do immediately was understand why these features maintain their shape in a ring which should be shearing with orbital motions.
The inner part of a ring orbits faster than the outside because gravity is stronger close to the planet. So how do the spokes keep from being pulled apart? No one knows yet. But Voyager did pick up a clue to what the spokes are made of as it sped away from Saturn at the end of the encounter. Here, the sun is shining through the rings, and the spokes look light instead of dark. You can just barely see them at the bottom, emerging from the shadow of Saturn. Dust in a sunbeam behaves like this. So Saturn's spokes are probably dust clouds, which still doesn't explain how they can keep their shape. But the biggest mystery for the Voyager astronomers was the pattern of the rings themselves. There are so many ringlets, the planet seems surrounded by a giant phonograph record. The rings are 40,000 miles wide and less than 1 mile thick. The scientists tried to determine the size of the ring boulders by shining Voyager's radio beam back to Earth through the rings.
Now, I can illustrate the concept of the radio waves from the spacecraft going back toward the Earth by means of a laser light in my hand now, which I will show how the intersection of the radio path and the ring plane draws out a path through the rings allowing measurements to be made of the characteristics of the particles, where the radio waves are sensitive to particles that are equal to its, what we call its radio wavelength, which is just this long, and larger particles. We can illustrate the way that the radio beams pass through the rings of Saturn and give us information back on Earth about the characteristics of the particles by this illustration of the laser light shining through various types of cloth. In this case, we're illustrating the effects of relatively large particles where the scattered energy going on toward the Earth is concentrated in several quite bright beams. If the particles are smaller in size and more randomly distributed, we get an effect of this type on the Earth. We can study that pattern to tell us more about the particles, their characteristics, and their sizes. If the particles are very small, it's more like the light passing through this wax paper where we have a more uniform spread of the energy.
In the outer ring, the boulders turned out to average about 30 feet across. In the middle, the rings are so dense that the radio beam was completely blocked. In the ring nearest to the planet, the boulders averaged about 3 feet wide. Voyager may also have answered a more fundamental question about the rings. What keeps them in place? Left to themselves, rings ought to spread out and disappear, with some of the material falling in towards the planet and the rest dispersing into space. What keeps Saturn's beautiful rings in line and so sharply focused? Voyager 1 found a critical clue at the edge of the main ring system, a tiny moon, invisible from Earth.
Now, here we see a small, rather insignificant satellite, roughly 100 kilometers across, but its importance lies in its location. It is orbiting just outside the bright ring system of Saturn. And ever since the nature of the ring system has been understood, that is, that the rings represent swarms of billions upon billions of tiny particles, there's always been the question, what constrains them? What keeps them from drifting off into space? And now we have the answer to that. It's this little insignificant tiny body orbiting just outside the bright ring system, that its own gravitational interaction keeps those particles in place. It kept the rings there for billions of years.
The thin, faint ring that's outside the main ring system has 2 moons keeping it in shape. They're called shepherd moons. This animation shows a simplified version of how shepherding works. The inner moon orbits faster than the ring. As it passes ring boulders, it pulls them along, speeding them up and landing them in orbits that are further from Saturn. The outer moon orbits slower than the ring boulders. The moon's gravity slows them down and drops them a little closer to the planet. The result of this process is that the ring boulders are pushed away from the moonlets. And Voyager found other strange gravitational interactions near Saturn.
Now, this peculiar-looking object here is one of the 2 so-called co-orbital satellites of Saturn. They're almost in the same orbit. In fact, their orbital radii are only about 50 kilometers apart. And these objects are more like 150 kilometers diameter, so clearly they're not going to be able to sneak by one another. They are closing in right now, and however, we expect there'll be some sort of a gravitational interaction that prevents them from actually colliding.
The outer moon is ahead, but the inner moon is catching up. As they close, the leading moon pulls on the trailing moon, speeding it up and boosting it to an orbit slightly farther from the planet. But the leading moon is slowed down and slides into a lower orbit. They do a do-si-do, switch orbits and pull apart. They'll dance again in 4 years.
But notice the very peculiar shape of this object. That strongly suggests that this is half of a single satellite. It was
impacted perhaps by a meteorite that split it in two. And these two satellites now, almost in the same orbit, are the two halves of some original satellite.
The Voyagers found the marks of a violent past on Saturn's larger moons as well. The most dramatic looking was Mimas, which is about 250 miles wide. Its surface is dominated by a single enormous crater, 80 miles across, caused by an impact that almost smashed Mimas to pieces.
We're going to pretend that these are comets, and we're going to fire these comets at rocks up there, which you're going to pretend are moons of Saturn. Now, actually, these shells only travel at about 1 kilometer per second, and a comet striking a moon of Saturn will be traveling at about 10. So the velocities are not quite right. What we're concerned about is the energy that we're putting into the satellite in comparison to the size of the satellite. And for that, our experiment is really quite satisfactory. All right, now we'll start with the smallest satellite, and then we'll work up to progressively larger satellites. All right, now let's look at the first case. The rock is gone, completely fragmented, and the fragments dispersed at relatively high velocity. And the second rock, which is here, we're just at the threshold of catastrophic disruption. Most of the rock is still here, but pieces are scattered about. If this had been the satellite, the pieces would just barely have separated, and the gravitation of the satellite would have brought them back together. Now we go to a satellite that's a little bit bigger for the same size crater, and we see that we formed a crater, in fact, and the rock was partly cracked, which we can see here, but pretty much it held together. And then we go to still a bigger object, and the satellite is now intact, and what we see is just the crater.
Mimas was just big enough to avoid destruction. Titan, Saturn's largest moon, got special attention from the hard-working Voyager 1 and its human controllers. Titan has a thick atmosphere, actually twice as dense as the Earth's. Astronomers have speculated that it might have fascinating chemistry, perhaps like the Earth during the time when life was first evolving. The mission planners hoped to catch a glimpse of the surface through breaks in the clouds. They flew Voyager 1 just 2,400 miles above Titan and programmed the cameras to cover the moon with high-resolution images. But the cloud layer was solid. The surface remained hidden. Voyager did better with its infrared detector, which measured light wavelengths the human eye can't see. The detector couldn't paint a picture of the surface, but it revealed some of the chemicals in Titan's atmosphere.
This funny wiggly line is just loaded with information. We start at this end with a rather smooth part of the spectrum. We come into these interesting features here, ending up here with methane, which we've just looked at in the laboratory. So this confirms what we've already known, that methane is in the atmosphere. Down here we find ethane and acetylene, and this peak is very exciting. This is hydrogen cyanide, which hadn't been discovered before. It's exciting because hydrogen cyanide is a molecule that played a very important role in getting life started on the Earth. You can polymerize it to make adenine, which is one of the bases in DNA, the famous double helix, which gets us all going. And you can make amino acids if water is present, which was true on the Earth, but not on Titan. And so I should make it clear that we're not saying that because we have found HCN in Titan's spectrum, that we think life is beginning on Titan, but we do think that some of the chemistry that happened on the Earth before life began is probably happening on Titan today. And if we can study it in more detail, we can learn something about pre-life chemistry on the Earth.
In Titan's upper atmosphere, high-energy particles from the sun slam into the hydrogen cyanide and methane and make them clump together into polymers, long strings of organic material.
So the substances that are forming high in Titan's atmosphere are some kind of organic material, which might be polymers of acetylene and hydrogen cyanide, polymers of the gases we detect in the spectrum. Then these things will gradually rain out of the atmosphere, the kind of slowly settling fog. We expect that the small particles will aggregate into larger ones and rain out onto the surface. Now, as they get closer to the surface, they'll pass through a region where methane may condense in the atmosphere. So we may have clouds of methane and methane rain, in fact, on Titan, because in some respects, methane plays the same role in that atmosphere that water vapor does on Earth.
With pools of thick organic soup on the ground, Titan may eventually have more to tell us about our own history than any place else in the solar system. Voyager 1 sacrificed its future to get so close to Titan. The course that NASA chose left it racing up out of the plane in which the major planets wheel around the sun. There would be no more planetary visits on its itinerary. Voyager 1's next known rendezvous is 41,000 years from now, with a star in the Little Dipper known as AC plus 793888. Voyager 2, following 9 months later, was supposed to swing behind Saturn and keep going to Uranus and Neptune. On August 25, 1981, Voyager 2 disappeared behind Saturn, all according to plan. But something went wrong in the shadow of the planet. Voyager emerged blind. Instead of more beautiful pictures, the camera saw black.
It's not there.
Frantic radio messages from Earth determined that Voyager's movable camera platform was jammed. At 3:30 in the morning, reporters were summoned to NASA's briefing room to hear the bad news.
And a few minutes later, we saw that the spacecraft scan platform, this platform that moves in azimuth and elevation, was not functioning properly. We've got very little data to work with.
Engineers tried to devise a repair strategy, and after 2 days, they attempted to move the platform again, very slowly. Out in space, a stuck gear started turning. Flickering images of Saturn reappeared on the screen.
Oh, okay. Yeah, Ellis has drawn what you should be seeing. The frame's upside down.
Voyager 2 would continue toward Uranus and Neptune, a 4.5-year journey. On Earth, NASA built bigger dishes on its radio telescopes to maintain communications as the distance to Voyager expanded by 500,000 miles a day. January 1986. Voyager 2 is finally approaching Uranus, a gas planet about 4 times as wide as the Earth. The camera platform has been checked repeatedly, and it seems to work. Voyager is as ready as it will ever be to investigate the planet that got knocked on its side.
Let me use this orange to tell you about Uranus. Uranus is different from the other planets because it's tipped on its side. Earth spins more or less straight up and down, which means that the sunlight is more or less falling on the equator and less on the pole. But Uranus is spinning on its side, which means that the sunlight is directly overhead at the pole and is exclusively falling on this one hemisphere. Of course, the year on Uranus is about 80 Earth years, and so in about 20 years, the orientation will change and the sunlight will be more or less overhead on the equator.
As Voyager approached, the spacecraft was facing one pole, The planet, with its moons and rings spread out around it, was like a spinning bullseye. But just 4 days before Voyager's swing past Uranus, the imaging system developed a new problem. Horizontal bars appeared over pictures of the approaching planet. Valuable information would be lost. What was wrong?
When I got home from Disneyland, where I'd been with the grandkids, my wife said somebody called and there was a problem on the spacecraft. So I came in about 10 o'clock.
They had concluded pretty firmly that it wasn't a ground problem. In other words, ground software or ground communications.
Engineers and programmers worked through the night. And finally, they found a single memory location that had failed, perhaps knocked out by a cosmic ray. They couldn't fix it, but they reprogrammed Voyager to detour information around the damage, and clear pictures reappeared on the screens. Uranus looked disappointingly plain, with nowhere near the atmospheric turbulence seen on Jupiter or even Saturn. If the atmosphere was boring, the planet's magnetic field more than made up for it. Voyager found the field pointing in a completely different direction from the planet's poles. As the planet rotates, it is constantly twisting its magnetic field. Uranus has 10 very faint rings. Each one is only a few miles wide. Voyager found shepherd moons around only one of the rings. Either there were others too small to be seen, or the scientists still don't understand what keeps rings stable. Backlit by the sun, the planet's brightest ring had the look of a phonograph record, first seen at Saturn and still unexplained. But the biggest puzzle was why the whole Uranian system is spinning on its side. Voyager may have found a vital clue when it discovered spectacular landscapes on Miranda, a small moon about 300 miles across. Miranda's surface is covered in grooves. There's a V-shaped white feature about 100 miles long. And this image shows giant ice cliffs more than 10 miles high.
It shows a fault which has broken the crust on what looks like a scissors fault, in which it's hinged back here and it breaks open like this. And the relief on that fault is of the order of 20 kilometers.
What appears to have caused all this is that Miranda was completely destroyed by a massive impact, and then reassembled from its original components.
Let's imagine this beaker represents a portion of Miranda, the whole satellite being a round feature like this, with the ice having risen to the top and the rocks having settled to the center when Miranda was warm enough at one time for this separation to take place. Now we know from study of the satellite surfaces and a calculation of the rates of cratering at different places within the satellite system that Miranda has probably been broken up perhaps a dozen times by very large impacts in the same time that the craters that we see on Oberon were formed. Now, if we imagine that the last time this happened, Miranda was smashed with a projectile, a comet nucleus, big enough to break the whole satellite apart, this nicely sorted arrangement of ice and rock would be distributed as debris that would go into orbit and would be mixed up in the orbit and spread out following the orbit of Miranda. Now, that debris won't remain there very long. It will want to collect back again into a satellite, rather quickly, as a matter of fact. But when it collects back in, the pieces that will fall into the satellite will come in different orders, icy chunks, rocky chunks, and so when we finish up, the final satellite will then be all mixed up and scrambled, looking quite different than it did at the outset. So we end up with a satellite then will look something like this. Now, of course, the satellite is not very happy in that state. The rocks do want to get back to the middle, and the ice wants to get to the outside. But it has to get warm enough for that to happen.
At first, after Miranda had been broken into pieces, the moon was spread out along its orbit as a swarm of boulders. Half of these were made of rock and half of ice. Gravity collected these boulders until a new moon was born. As the boulders crashed together, Miranda heated up, just barely hot enough to melt the ice and let most of the rock sink through to the moon's core, while the lighter ices rose to the surface. But the ice refroze so quickly, the surface was left rough, with deep grooves and high cliffs, like molten lava that solidifies before it can spread out. This movie, which shows a flight over the surface of Miranda, was made from Voyager images and shows its rough, jumbled state. Impact catastrophes may also explain the whole of the Uranian system. Perhaps once Uranus and its moons orbited as the other planets do, but a giant comet knocked Uranus over. The orbits of the moons were disrupted, and they crashed into each other, creating a cloud of debris that settled into a ring of material orbiting above Uranus's new tipped-over equator. This ring then condensed into a brand new collection of moons. Later, other comets may have passed through to smash these moons in turn. On the larger moons, gravity smoothed out the wrinkles and helped ice separate from rock, but Miranda is small enough to preserve the signs of destruction and reassembly. At every stop along its grand tour, Voyager had seen the results of titanic violence in the early solar system, but nowhere as vividly as here at Uranus.
Where did these impacting bodies come from that pummeled the satellites of Uranus and probably tipped Uranus itself over on its side? To answer that question, we have to go back to the origin of the planets. And here we have a diagram showing the planetary regions we see it today with the orbit of Neptune, Uranus, Saturn, Jupiter, Mars, and the orbit of the Earth and the close planets and the Sun itself just in this tiny region in the center. And all of these dots in this region out here represent a swarm of small bodies of ice and rock out of which Uranus and Neptune accumulated. These bodies were perturbed by the growing planets. As they were accumulated into the planets, most of the objects actually were thrown out of the solar system, and only about 5% fell onto the planets themselves. But the swarm of small bodies, which we call planetesimals, continued to buzz around the planets in this region for about 500 million years. And so long after the planets were formed, there was still an intense bombardment. Somewhat less than 10% remain today in a huge cloud surrounding the sun, and as passing stars go through or near this cloud, they perturb a few of them which fall down toward the sun to the neighborhood of the Earth, and we see them as comets.
From Uranus, Voyager 2 sped on toward the last gas giant, Neptune, 3 more years of travel away from the sun. In August 1989, the team members assembled under the television lights for the last Voyager encounter. Many of them never expected Voyager would survive this long. Jupiter and Saturn would have been enough. Uranus was a bonus. Now Neptune is a wondrous gift. With sunlight 900 times weaker than on Earth, the scientists thought Neptune's atmosphere might be sluggish and dull. Instead, they found the fastest winds in the solar system.
So it was a very pleasant surprise to see storms, to see them move, and in fact they move very fast, about 700 miles an hour.
The most dramatic surface feature was a huge dark spot, a storm bigger than the Earth. The scientists made a sequence of images so they could see what the spot was doing.
So we put together a movie in which the great dark spot always remains in the center of the field of view. And in these frames, you can see things changing, but you can't quite tell whether the spot is rotating or not rotating. When we play it faster, all of a sudden it snaps into focus. To me, it looks like a rolling mass of blue pizza dough, and you realize that the great dark spot is rotating counterclockwise at rather high speeds. Now this image, I like to play it over and over again and compare it with what we get in our computer simulations. It's the key to understanding the weather on Neptune.
On such a cold planet, there may be so little friction that less energy is needed to generate ferocious storms like the Great Dark Spot. More surprises were waiting for the NASA team when Voyager reported home from Triton, Neptune's largest moon. Triton was the coldest world on Voyager's grand tour at -400 degrees Fahrenheit. But its surface was studded with signs of recent activity. And for the second time in the Voyager mission, photoanalysis revealed active eruptions.
The exciting thing about this image is that it's not a perfect crescent. If you follow the curve along here, you'll see there's a bump. In fact, that extends from here to here. And now what can make a bump like that? Why don't I see a nice smooth curve? That means there's something high that is still getting sunlight, although the ground around it is in darkness. Now, what can be that high? Mountain ranges, perhaps. But when you measure how far this bright spot is from where you know the ground is in shadow, you'll find that this is 13 kilometers high. That's far too high for any of the terrain that we saw on Triton. So from that I knew this really needs to be something in the atmosphere. So this was essentially a discovery that there are high clouds over this area of Triton's surface.
The clouds turned out to be gigantic geysers, spraying nitrogen snow and carbon dust 200 times higher than Old Faithful on Earth. The icy eruptions of Triton and the cold winds of Neptune capped a journey full of unexpected drama and alien beauty.
The lesson is that the universe is far more beautiful, complex, and interesting than we ever imagined.
Both Voyagers are now heading for interstellar space. They are still in touch with Earth, but their electric power is fading. Sometime around the year 2018, the two probes will stop calling home and lapse into eternal sleep. Probably no intelligent being will ever see them again. But just in case, NASA equipped them for one final mission. On board each Voyager, squeezed in among the telescopes and radio equipment, is a copper record containing the sights and sounds of humanity and carrying our greetings to anyone who may share this vast universe we are only beginning to explore.
Shalom.
Bonjour tout le monde. تحياتنا للأصدقاء في النجوم.
Namaskar. Bishe Shanti Hok.
Hello from the children of planet Earth.
Funding for NOVA is provided by Lockheed, a bold new force in systems engineering, management, and technology services for defense, space, and industry. And the Johnson & Johnson family of companies, supplying healthcare products worldwide. Major funding for NOVA is provided by the financial support of viewers like you. For a transcript of this program, send $5 to this address or call 212-227-READ.
This is PBS.